All right. I think that's going. Lights on. Okay. So last time we finished section 1.1, which was on topological spaces. And we covered, once again, the definition of a topology. This is the last time I may go over the entire definition of a topology with you. After this, I may expect you to know it. So let's remind ourselves of what exactly a topology is. So tau is a topology on some set X, if and only if it satisfies these three properties. Without looking, do you remember what the three properties are? What's the first property? Has to include the empty set and the entire set X. That's the first property. Second property is?
The intersections of... There's a set for every intersection. Yeah, so the intersection of every set has to be open set within the topology.
Almost. Take any finite number of open sets, intersect them, and that set has to also be in the topology. Has to also be an open set. So not just any two sets intersect them, it's in the topology, that's true. But any finite number of sets intersect them, and it has to be in the topology. Unions, it's a little bit more relaxed. So for unions, it's any arbitrary union, finite or infinite. Because some topologies are infinite sets, right? So I could grab any arbitrary subset of those, possibly an infinite one, union them all together, that better still be in the topology. So, perfect. Let's go over that now with writing here. So tau is a topology on X if and only if the empty set is in tau, or in other words, the empty set is open, and big X, that's a capital X, is in tau, or in other words, capital X is open. Property 2. If U1, U2, ... UN are all in tau, or in other words, if we have finitely many open sets, then the intersection of those sets has to also be in tau. The intersection from I equals 1 to n of U sub I has to be in tau. Or in other words, we have U sub 1 intersected with U sub 2, intersected with U sub 3, intersected with U sub 4, ... intersected with U sub n. That's what this notation is saying right there. Make sense? So the intersection of all those things has to also be in tau. And then finally, the third. Remember that the power set of X is all possible subsets of X. Sorry. I think I wrote that wrong last time too. Can't believe I did that. Take any arbitrary collection of sets out of tau. Take any arbitrary collection of open sets, possibly finite, possibly infinite, then the union of all those sets has to also be in tau. Make sense? Okay, so those are the three properties for it to be a topology. And then we call capital X together with tau, its topology. We call that a topological space. It's a common thing, we call mass structures. A common process we go to is we take some state and we pair it with a set that somehow gives that set structure. So we take a set and we pair it with some other set that somehow gives this set structure, and we call it a space of some sort. So this is called a topological space. If any of you took topology from me, we did a sample space for probabilities. We had the set of all possible outcomes together with their probability function. That gave us a sample space. Did I not do discrete math with you? In discrete math, yeah, we talked about sample space. Same thing. So something space, vector space, when we get to that, it'll be a similar thing. A set of vectors together with some structure. So common thing we do. Anyway, so a topological space. It's a set together with some topology on the set. Some topology which gives that set structure. Okay. We went over some basic topologies. We had the trivial topology. What's the trivial topology? Go ahead.
It's X
together in a set. It's a set containing X in the empty set. That's the trivial topology. So for any set X, this is a topology on that set. We also have the notion of the discrete topology on X. What's the discrete topology on X? The power set of X. Power set of X. The set of all possible subsets on X. Yes, the empty set is a subset of X. Everything in the empty set is an X. The empty set is a subset of any set A you choose.
So the power set of each set always has the answer.
Correct. And then we had the finite complement set. Remember what the finite complement set was?
I remember what a complement is. I can't remember.
What's the complement of a set?
Complement of a set is all the numbers that are not in the set.
All the points not in the set. Could be numbers, could be whatever set we're talking about. When it's arbitrary, we say points. We're members. So U can always be expressed as X minus F, where F is some finite set. This is how we represent each open set. Every open set can be represented as X minus some finite set. That finite set is going to be the complement of U. F is everything not in U. Take X, get rid of F, that's how you get U. So F is everything not in U. If F is finite, U has a finite complement. So it's a set of all those sets. Yeah, we proved that last time, that the finite complement topology is a topology. We proved if X is also a finite set, then the finite complement topology is the same thing as a discrete topology. That was one of the proofs we did last time. All right. We talked a little bit last time about one topology being finer than another topology, or one topology being coarser than another topology. So if topology 1, tau 1, is a subset of tau 2, which of those is the finer topology? Tau 2 is the finer topology. It has more pieces than tau 1. Every piece tau 1 has, tau 2 has, but tau 2 has even more pieces than tau 1. So tau 2 is finer than tau 1. Tau 1 is coarser than tau 2. And if tau 1 is a proper subset of tau 2, so they can't be equal, then we say tau 1 is strictly coarser than tau 2, and tau 2 is strictly finer than tau 1. Perfect. And then the big theorem that we proved last time. So what was the theorem? Theorem 1.4, it said, let X be a topological space. Maybe pause there for a second. I just barely called X a topological space. Isn't a topological space an ordered pair X with tau? This is a topological space. Why did I just call X a topological space? Because we're lazy. And so when I call X a topological space, you instantly understand, oh, he's talking about some topology on X, and he's going to use tau now without explicitly saying what tau is. So it's just me being lazy. The only reason I'm introducing that is because if you're reading the book, the author does that all the time. He says, let X be a topological space. It's understood that we mean we're really saying that this is our topological space, and our set is X, and tau is a topology on X. So let X be a topological space. You're instantly thinking in your head, okay, that means I can use some tau, which is a topology on X. And let A be a subset of X. Then A is open if and only if for every point in A, there exists some open set in tau such that X is in that open set, and that open set is a subset of A. Let's draw a picture for this again. So here's big X. There's our whole universe. A is some subset of big X. So here's A. A is an open set if and only if for every point in A. So pick any point in there we want. We'll call it little x. For any point in A, there exists some open set. I'm going to start using dotted lines to talk about open sets, and you'll see why in a second. You'll understand why we start doing this by the end of today's lecture. There exists some open set U sub X containing X, where U sub X is a subset of A. If I can do that for any point in A, I can find some open set around it that's a subset of A, then A has to be an open set. Big picture, how did we prove that? We just took the union of all those sets around each point. The union of all those open sets has to be an open set. And so since A is a union of all those open sets containing the points, then A is an open set. So now, one more time. Here's A. If I can show that for any point in A you choose, doesn't matter which point it is, X, there exists some open set containing that point, call it U sub X, where that open set is a subset of A, then A has to be an open set. And ultimately we showed that A was equal to the union of all those u sub x's for each little x in big A. Union for each little x in big A, its corresponding u sub x. Take the union of all those. What do you get? You get back A. Since A is a union of open sets, A is open. That was a big picture idea of how we proved it. If you want the details spelled out for you, you'll have to go back and watch last lecture. Okay, so that takes us to our next section now. Our next section, which is on a basis for topology. So I told you sometimes it's really tedious to try and talk about the entire topology. These topologies can be massive, and it can be hard to describe the entire set of open sets. It can be difficult. So we have this notion of a topology, or of a basis for a topology, which makes it easier to understand what the topology can do. And I gave you an analogy last time of thinking about, imagine our topology is a set of all possible Lego structures you can build. How many Lego structures can you build? An infinite number, right? We're not going to put a limit on pieces. An infinite number. Now, there's a finite number of types of pieces, though, right? So I could just say, our topology is all the possible things we can build using any of these pieces as much as we want. So here's our finite number of pieces. I write out, maybe there's 2,564 different types of Lego pieces. So I say, here's each of the 2,564 different types of Lego pieces. What do I mean by Lego structures? Anything that you can build with any arbitrary collection of these things. That's kind of what a basis is. A basis is going to be a collection of sets, and our topology is going to be any set you can build choosing from those sets. And you can pick them as much as you want and union them together, which is going to be like hook and Lego pieces together. And any set you can build, we're going to call that an open set. So that's how a basis is going to help us talk about topology. So let's give the exact definition of what a basis is. It's going to take a sec first to get to the point where we prove that we can use a basis to create a topology. That's going to be the big proof of today. So definition. Let beta, always use beta for a basis, and always use capital B for the elements in beta. And our capital B's are going to be the things that we use. They're going to be like our building blocks, our basis elements. They're going to be like our building blocks. So let beta be a collection of subsets of X. So what's everything in beta? Everything in beta is a subset of X, right? And we're going to be unioning those subsets of X together to create our topology ultimately. So let beta be a collection of subsets of X. We call beta a basis for a topology on X, provided that it satisfies these two conditions. Condition 1, for every little x in big X, there has to exist some b in beta such that X is in B. Or in other words, well, I don't know a better way to say that. So beta here is a collection of subsets. For every point X in big X, it has to show up in one of those sets. If beta is going to be a basis on X. So for every little x in big X, there has to exist some b in beta such that X is in B. So every point has to show up somewhere in beta. Every point X has to show up somewhere in beta. It has to show up in at least one of its basis elements. Maybe multiple of them, but at least one of them. That's the first condition. First condition makes sense? Second condition. Second condition says that if B1 and B2 are basis elements with some intersection, so if we have two basis elements, two sets that intersect in any way, so if B1 and B2 are basis elements such that their intersection is not empty, so in other words, there is something in their intersection, call it little x, then there must exist some third basis element in beta, such that X is in that basis element, that's a B sub 3, where B sub 3 is a subset of their intersection. Let's draw this out pictorially and then read this one more time. So here's B1, here's B2, and they have some intersection. Can you see my picture good enough? That's a B2 right there. So here's B2, here's B1. There are those two sets. Notice that they have some intersection. label, since they intersect, then there must be a point in their intersection. So pick some random point in their intersection, call it little x. If beta is a basis, then there must exist some third basis element, b sub 3, like that. There must exist some third basis element, b sub 3, such that x is in b sub 3, and b sub 3 is a subset of the intersection of b1 and b2. Got a bit going on there. Okay, so if those two conditions are satisfied, then it is a basis. We call the members of beta basis elements. So the b's here we call basis elements, and the beta we call a basis. So the basis is a collection of subsets. A particular subset we call a basis element. So b1 is a basis element, b2 is a basis element, b3 is a basis element. That's the language I'm going to be using.
Why exactly do they call it basis? Is it really just a subset of the overall X?
They call it a basis. Typically, we call something a basis when it can be used to generate the thing we're interested in. So if you're in a common basis would be, if we're talking about R2, the plane, you ever work with vectors? So two basis vectors in R2 is the basis vector pointing that way and the basis vector pointing that way. 1 unit length each. Any vector you can create can be created from combinations of those two vectors, scaling them up or scaling them down. So I can use those two vectors to generate any vector in R2. So those two vectors would be a basis for a vector space on R2. Similarly, this beta here is going to be a basis for a topology on X. We'll somehow be able to generate a topology from this basis. So that's why it's called basis. The word basis shows up a lot in math in different fields. It just means the structure we care about can somehow be generated from these things. Okay, any other questions before we move on to, well, another definition, then some examples?
Yeah. I'm not understanding why they specify that B3 is a subset of the intersections that just conjugate. Why are they specifying B3 there?
There has to be some basis element that contains a point. Oh, you're saying why don't they just say that and their intersection has to be a basis element?
That X is an intersection. That the intersection counts as basis, yeah.
So it turns out that the intersection is going to be a basis element.
Okay.
That turns out to be true from this definition.
So why do you need to point out that X is also a basis element?
Well, because we want B3 to also be a basis element. It's going to make it easier to talk about things.
Oh, so just
Yes, it's like we're trying to be apply as little restriction as we can to still get what we want. Because when I have two arbitrary sets intersecting, it's pretty easy to find a small set that's easy to talk about. So let me give you an example. In R2, so I might have an open set that looks something like this. And I might have another open set that looks something like this. They have an intersection, and I've got an X there. It might be kind of hard for me to describe exactly what that space is. That's a hard space to describe. But it's real easy for me to put a little circle around that space and describe the circle containing that point.
isn't it mathematically that space is a bunch of dots, a bunch of X's?
It's a bunch of X's, but there's no nice way for me to tell you what it is. But it's real easy for me to say, okay, we can put a little circle around it that for sure doesn't go out of that space. It's real easy to talk about that circle.
It's not easy to talk about what's in it. The only thing in that circle right now, X.
No, every point on the whiteboard is a point.
Yeah.
I just picked an arbitrary point that we care about. So pick an arbitrary point that we care about. It's real easy for me to get a little circle around that point and talk about that circle.
But it's still just a bunch of X's. Mathematically, you're not seeing a picture. It's just a bunch of data and different bases. Why is drawing a circle compared to having that weird squiggly shape?
It changes something in ease of our ability to talk about it.
So just zooming in. That's
No. Let's say that I knew the exact coordinates of this point, right? And we'll say, let's pretend that that x had coordinates exactly x equals, geez, I think I'm still, no, probably left the camera there. Let's say x is equal to exactly the point, we'll keep it really simple, 2, 1. Okay? And let's say that the radius around x that I care about, r, is exactly 0.01. So then, this ball around it, I can easily describe. And it's going to be, that ball is going to be the set of all y in R2 such that the distance, this would be our distance function, from x to y is less than our radius, 0.01. And those are all the points that will be in that ball around that point, where this distance function is a Euclidean distance function between 2 points, which we can, again, explicitly describe. So we have a clean way of talking about that.
So, topology and geometry, there's geometry and topology. I was seeing this as you were just trying to make sense
No.
of drawing a picture.
There is not geometry in topology. Topology is a weaker structure than geometry. I'm just giving you an example.
So, if an example, how's our distance? If
A distance doesn't necessarily give you a geometry.
Okay. How's our distance between 2 points on data sheet?
Well, we can define some function and call it a distance function. We'll get to what's called a metric space. And then this will be an easier conversation to have. But yes, you could just say, and their intersection is 1. Ultimately, though, I'm going to want, how's a nice way to say this? Most of the topologies we care about, we need to get to an example in R2, and then this will be easier to explain why it's so useful. Sorry. I don't know how to give good intuition before we go over any topologies where it makes sense to think about this way. But yeah, it turns out it's much, much easier to just have this be a subset of that than require it to actually be equal to that. Because figuring out what exactly that's equal to can be hard, whereas finding a subset of that can be much, much easier. That's, in practice, what it's going to come down to. Okay. Did I erase something important? Oh, I just erased the picture I had to help us see this. So if this is B1, and this is B2, B1 and B2, they have some overlap. So there is some point in here in their overlap, little x there. And so we require that there must be some third basis element, B3, containing x. And maybe B3 is the entire intersection, maybe it's smaller. But we just require it to be a subset of the intersection. Maybe the whole intersection, maybe smaller. So we can use a 1 equal to it even if we want. Okay. Now, definitions for the topology that generates, and then we'll go over some examples. So, if beta is a basis for a topology on big X, then the topology generated by beta is the empty set together with any union of basis elements. And those are our open sets. The empty set together with any union of basis elements. We're going to prove that that gives us a topology. That's going to be our next theorem that we do here. But first, let's do some examples, and we'll go to that theorem. But does the definition here make sense? Okay, so
That would lead all the way up to X.
yes, just union every basis element together. Because our first condition here, our first condition says that for every little x and big X, it has to show up in some basis element. So union up all the basis elements, you get x. So the union of beta is x. Okay, so our first example is going to be, let x be any set, then beta equal to the set of all singleton sets is going to be a basis for a topology on X.
What was that word? Did you say singleton sets?
Oh, sorry. A singleton set is a set that only contains a single element. That's what, yeah, sorry. So beta is equal to the set containing X for each little x in big X. really concrete example for a second here. So we'll say that big X is equal to the set A, B, C, D, right? Then we're saying beta is equal to the set containing the set A, comma, B, comma, C, comma, D. There's our basis. Now what's the topology we generate from that basis? The topology tau that we generate is the empty set together with any union of these sets. So I can union this set with this set, which gives me the set containing A. I can union this set with this set, which gives me a set containing B. And I can get the set containing C, the set containing D. Notice that every basis element is always an open set. Because you can just union it with itself. Were you saying something?
I was going to say, so wouldn't it be the power set?
Oh, it's just a power set. Perfect. So we could list it all out. We don't want to list them all out because how many would we have to list? No. Not that big.
It goes up exponentially though.
2 to the 4, just 16. Not too bad. But we don't want to do that. You're probably trying to remember the number of possible topologies we can make on a set. Anyways, I don't want to list them all out, but yes, it's just a power set on X. And that's the topology that this one happens to generate. So if you do the basis elements of all singleton sets, it generates a discrete topology every time for whatever set you're talking about. And we already talked about that. I think we did a proof of that once. That if every singleton set is an open set, then your topology is always a discrete topology. I think we already proved that. And so, if your basis elements are all singleton sets, and all your basis elements are also open sets, then that instantly gives you the discrete topology. So, that basis automatically generates a discrete topology for any set X, doesn't matter what it is. Not just in this special case we have written here. Make sense?
Now, the basis, it doesn't always have to be the set of singleton sets.
This is an example of one basis on X.
That's why I want to know if it could have a set that might include multiple elements, but eventually all the sets at least contain one of the elements.
This is one basis I could create it on X. The topology generated by this basis every time is a discrete topology. So a basis generates one and only one topology. So this basis generates one and only one topology, namely the discrete topology. We'll come up with different bases for different topologies, and we'll see a bunch of them in action. So yeah, this is just one example of the type of topology you can create. Let's look at another one. On R, remember that's the real number line, beta is going to be the set of all open intervals you can make A, B, where A is a number smaller than B. Let's make sense of this. We're saying, so here's the real number line, zeros right there, whatever. Here's A, here's B. The open interval from A to B is a basis element. And any union of those open intervals you can take is going to be an open set. So we call these open intervals. And any open interval is an open set.
What do you mean by interval here?
That is an open interval. That one's called an open interval. This is called a closed interval. Right? So, open interval, right there. So beta is a collection of all possible open intervals that you can make. The open interval from -16 to 2,586. That's one of our basis elements. The open interval from 0 to 1. That's a basis element. The open interval from 1/3 to 1/2. That's a basis element.
This basis will create one topology.
And this basis generates one and only one topology. And we call the topology generated by this basis the standard topology on R. This is the topology you're doing an analysis of when you're studying calculus. This is the topology you use. So let's get a feel for this topology. First off, is the empty set in our topology? How do you know?
It has to be or else it's not a topology.
Right, so how do I know that the topology generated by beta includes the empty set? We're just calling it topology. I haven't proved that the topology beta generates is in fact a topology yet. So how do I know that the empty set's in there? Because a topology generated by a basis is the empty set together with any union of basis elements. Okay, so that's how we know that the empty set's in there. Is the entire set R in there? If tau is a topology generated by beta.
Wouldn't it eventually go for that? We just combine every greater than less than.
Yeah, if we union up every possible open interval you can create on the real number lines,
We're not doing that
on the
yet.
real number line. Huh?
We're not doing that yet.
Beta is a set of all possible open intervals you can make.
Well, that's the key.
So the union of beta is obviously equal to R. Now we could have done it a different way. I could have said, consider this. Consider the union. Find a place to draw. Consider the union for all little. Consider the union for all little x in R of x minus 1 to x plus 1. You understand what this is? Can't draw anywhere. Let me move the camera so I can start using that space over there, I think.
I actually apologize. I spaced out for a second, and I wasn't paying attention to the explanation on the logic of how this beta was created.
Okay. This beta is the collection of all possible open intervals a, b, where a is a number less than b. So here's some things in beta. The open interval 0 to 1, that's in beta.
How can I?
The open interval pi to 2,768, that's in beta. The open interval 3 to negative 2, that's not in beta, because that doesn't make sense. Because that has to be less than that. So beta is a collection of all possible open intervals we can make. So what I wrote right here, let's union up for every x in R, the open interval centered at x going one to the left and one to the right. So if x is right here, then x minus 1 is going to be one unit to the left, and x plus 1 is going to be one unit to the right. We're talking about this open interval. Do that for x, and now do that for what if x were right here? Now its open interval goes from here to here. What if x were right here? Now its open interval goes from right here to right here. Take for every x in R, the open interval around it, 1 unit wide, union all those up. What do you get? All of R. Right? There's another way we could talk about, show that R is in there. Plus R itself is an open interval, so by its definition it's in there. Actually, let me think a little bit more carefully about that. I didn't specify, but I think A and B have to be real numbers. Infinity is not a real number. So no, R is not a basis element. I don't think. It was a little too fast and loose when I wrote this, and now I want to go double check. Because did they say any open interval, or did they actually write it out like how I wrote it out? let beta yeah, the entire set R is not. So A and B have to be elements of R. Okay. But nonetheless, we can generate R a ton of different ways. So we know R for sure is in our topology, right? What other things are in our topology? Any union of open intervals. So 1, 2, 1 comma 2, union together with 17 to 29. That's an open set in our topology. So any union of open intervals. So that's all the points from 1 to 2, these points, together with all the points from 17 to 29, those points. Any union of open intervals is an open interval, is an open set.
So if you were to write that 1, 2 as a set, that same thing except it's squiggly lines.
No, no, no. This is not the set 1, 2.
Real
This is a set of all x in R such that 1 is less than x is less than 2, not including 1 and 2.
These sets are infinite.
Each one of these open intervals are infinite. Every open interval is infinite. If AB is an open interval, there's an infinite number of elements between it. Yeah?
That's just so many numbers.
It is a lot of numbers. Hard to think of more. Okay. So that's where topology is.
Just that?
Yeah, just that. And you'll notice it satisfies all the rules for our topology. Because now I know that any open set is a topology. What happens when I take an open set and I intersect it with an open set? What do I get? An open set. If I take an open interval and I intersect it with an open interval, what do I get? An open interval, which is an open set. Right? If I were to look at, so looking at our, does this topology satisfy all these properties? Obviously the empty set's in there and the entire set R is in there. Obviously the union one's going to work because each open set is already a union of basis elements. And so if I union up a bunch of unions of basis elements, I get a union of basis elements. So the only one you really got to think about is the intersection one here. Does any intersection of these kinds of sets, is it still going to be a union of open intervals? Take a union of open intervals, intersect them, do you still have a union of open intervals? And the answer is going to be yes. So let's give you an example. One possible open set I could have, here's my real number line. One possible open set I could have is all the points from here to here, union together with all the points from here to here. I'm drawing it above because I need to too. But we're saying transpose that down onto the real number line. You understand what I'm saying? And another possible open set could be all the points here together with all the points here, together with all the points here to here, right? And when we intersect those, do we still have a union of open intervals? So when I union this with this, I'm left with the open interval from here to here. Oh, sorry, not union, I mean intersect. When I intersect this with this, what do I get? I get the open interval from here to here. Let's see, this one doesn't overlap any other one. When I intersect this with this, we get the open interval from here to here. And when I intersect this with this, we get the open interval from here to here. And we still just get a bunch of open intervals. So when you intersect some union of open intervals together with some other union of open intervals, you just get a union of open intervals. So all our open sets in standard topology are anything that can be written as unions of open intervals. Go ahead.
I'm going to figure out a word this.
Okay.
Because with that first example, we have multiple sets in the basis. If we put that same,
This has infinite sets in its basis.
yeah, but they're all unions to create one thing. you were to take that in one set and then duplicate that set over, so there are two of those sets in the same thing, would that be the power set? So included everything basically. It's kind of weird, but I'm wondering why that's not power set while this is.
Okay, so one thing that you can never get from here is a set containing just one. This is not an open set.
That's fair.
Here's another set that you can't get. You can't get the closed interval 1 to 2.
Yes.
Here's another set that you can't get. The open interval from 1 to 2 included.
That's a 0, but yeah.
Oh, sorry. There's another set you can't get. So there's a bunch of sets that aren't open.
So why can't you just have
The set of all integers is not an open set.
Why can't you just have the interval from open 17 to open 29? Just that. Why can't just
You
that
can.
be the topology?
Open from what?
17 to 29.
17 to 29.
Is that itself an topology?
This is a basis element. This is one of our basis elements. This is one of the things in here.
What if you had 17 to 28 and 28 to 29? But those union those together, why is that not in the topology? You have to union it with everything because they're in the same set.
This is one basis element. This is another basis element. These are two of the things that show up in beta.
Because you union them together to create another base element.
Forget the fact that we're unioning them together for a second. Just, this is one of our basis elements.
Yes.
And this is one of our basis elements. We have an infinite number of basis elements.
Yes.
Our topology is composed of any possible set you can get unioning these types of things up together. Any possible set you can get, take that, put it in tau. That's our topology.
And a topology includes one of the base elements.
Every basis element is going to be in our topology.
Oh, okay. You just didn't write it. Okay.
Every basis element is always in the topology.
That's what
Yes.
you're trying to say.
So for all B in beta, B is going to be in tau. That's always the case. Because B is a union of basis elements. Union it together with itself. There you go.
So that's power set.
No. This is just a set of all open intervals. The power set gives us a set of all possible subsets we can get. So something that we cannot get in this topology is a set just containing one. Or the naturals.
Fine.
So the naturals, well, we'll do the integers. So here's 0, here's 1, here's 2, here's 3, here's -1, here's -2, here's -3, right? We want to get just those points. I don't want the thing right next to 1, and I don't want the thing right after 1. So I need to come up with, if I'm going to include 1 as a point, the only way for me to do that with my basis is to pick some open interval that contains 1. But no matter how small of an open interval you choose that contains 1, it's still going to contain infinitely many points before 1 and infinitely many points after 1. Doesn't matter how small I make my open interval around 1, I still got infinitely many points after and infinitely many points before. I can't get just 1 with an open interval.
Why? Why not?
So you might say, you might be thinking to yourself, why not the open interval 1 to 1? Okay, by definition, this is equal to the set of all x in R such that 1 is less than x is less than 1. What are all the numbers greater than or equal to 1, or greater than and less than 1? The empty set. So the open interval 1 to 1 is the empty set. And so it didn't get 1.
So if you made that less than or equal to.
So we got to make it, we got to pick something less than 1 if we want to get 1 in there, and something greater than 1. And so it doesn't matter if I would have picked, okay, let's pick 0.99999, comma, 1.000000001. we still got infinitely many points. Doesn't matter how zoomed in you get. So we can't get just 1. We can't get just 0. We can't get just -1.
One is in there somewhere.
1 is in this open interval. So we got 1, but we didn't get 1 by itself. We were trying to get just the integers.
Right.
So we were trying to come up with a way to just get 1 and nothing else.
And we don't allow putting
We don't allow infinity
because
terms.
I understand that like 0 or 0.999 to infinity is 1.
Right. So then you're just doing 1 to 1, and that doesn't fix anything.
If I'm saying you can't include the term infinity, like you can't say I'm going 0.9999 ...
You can if you want. So you're saying, let's look at the open interval, 0.9 with a line above it,
What does that mean?
repeating forever,
Yeah.
to 1.0 with a line above it. I guess is what you're trying to say?
Well, there's a 1.
There's a 1 at the end of infinity.
True. No, you can't do that.
You're going to end up with the open interval 1 to 1, same thing, which is equal to the empty set.
You're right. Is there a way to say 1?
Should probably show that really quick to these guys. Why 0.9 forever is the same thing as 1. You've done it? Okay. So
One time.
we can do it really quick. It takes 10 seconds. Let x equal 0.9 repeating. Then 10x is equal to 9.9 repeating. Subtract the 2, you get 9x is equal to 9. So x is equal to 1. Okay. Anyways. So there's no way to get just 1 by itself. No matter how small the open interval you pick around 1, you're going to get infinitely many points.
Well, hold on. What if I did provided a mathematical operation where I do 0.9 minus? Oh shit! Still can't do it.
So here's something that you might be tempted to do. I'll tell you how I thought I tricked the teacher the first time I took the class. And here's what I said. I may get just a 0.0. Here's what I told them. I can get just a 0.0. I'll show you how. I'm going to do the intersection from I equals 1 to infinity of the open interval -1 over n, comma 1 over n. Now, you guys haven't done calculus yet, so that might be something weird for you to do. But in other words, I'm going to take -1 over 1 to 1 over 1 and intersect that with -1/2 to 1/2 and intersect that with -1/3 to 1/3 and intersect that with -1/4 to 1/4, dot, 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 on and on forever. Keep intersecting forever and ever and ever. The only thing in that intersection is 0. This is another way to write the set containing 0. So this is, in fact, equal to the set containing 0. So I thought I got it. I didn't get it. Here's where one of those rules for a topology comes into play. You can only take a finite intersection of open sets. This was an infinite intersection of open sets. That's why it's different. You can take an infinite union, you can take any union you want, but when we're taking intersections, we're not allowed to do infinite intersections. Otherwise, the set containing just 0 would be an open set, which is not what we want. So that's why that second condition is only a finite intersection of open sets is an open set. So that's how I thought I could trick them. But turns out you can't trick math. I always lose. Okay. Any more questions on the standard topology? That was over here. We're going to be working with this topology a lot, so it's a good one to get comfortable with. It's called the standard topology on R. This is the topology you're using when you do calculus. So it's one that we're going to use as an example a lot. So it'll come up over and over again. It'll take you time to get completely used to it, but with time, I think you will. So good on that. I think this one will make a lot more sense once we get to R2 and talk about the standard topology on R2. And then on R3 and R4. Okay, so with that, we got to move on to, I have a lemma I have to prove, but I have to prove it by induction. Yeah. And we're not going to prove that proof by induction works in this class, because typically if you were in this class, you had that proved in an earlier class. It's not that we shouldn't prove it, it's that most people going through this material, it's assumed you got that somewhere else. So for example, typically you take discrete math before this class, and it's something you prove in discrete math. So we don't have the time to prove that proof by induction works in this class, but you need to get the idea for proof by induction. That's the important thing. So I'm going to tell you, I've got some secret set. Some secret set. And I tell you that it has some number in there. 3. 3 is the only thing I tell you is in there. I don't tell you what else is in there. But I tell you that this set has a special property. The special property is anytime k is in there, that implies k plus 1 is also in there. So anytime you can find some integer k in the set, then you know k plus 1 is also in the set. So what else do you know is in this set? 2? I don't know 2's in there. 4. I know 4's in here.
Right.
What else is in there? 5. What else is in there? 37, but let's not skip. 6, 7, 8. All the positive integers starting at whatever my first integer was that I knew was in there. So that's what we do by proof by induction. I prove, starting with some integer, like 3 or 2 or 1. Notice that my starting integer, it didn't really matter which one it was here. I just reveal information that you have some starting integer, in this case 3, and then I reveal that it has this property. And then you can determine an infinite number of numbers in there after that fact. Make sense? So if I had some statement about numbers, and I prove to you that the statement is true for the number 3, and I prove to you that anytime the statement is true for some number k, it's also true for k plus 1, then you know that not only is the statement true for 3, but it's also true for 4, and 5, and 6, and 7, and 8. ... So we're going to do a proof by induction. I'm going to say that some property is true for every integer starting at 2. So I'm going to show you that some property is true for every integer starting at 2. And then I'm going to show you that if the property is true for the integer k, that also implies it's true for the integer k plus 1. And therefore, that property is true not only for 2, but also for 3, and 4, and 5, and every positive integer from 2 onwards. That's the thinking behind a proof by induction. They're actually one of your nicer math proofs. One that you hate to see the first time you see it, but after a couple times, you'll love it. Because if you can prove by proof induction, that's one of your easier ways to prove something. So it's a common thing with people who are familiar with math to say, oh, you just prove that by induction. And they say, oh, okay, yeah, that's easy. You'll get to that point. Sounds impressive at first, but it's really not. Okay. Oops, hit my mic. It's going to be annoying when you listen to it. All right. Our proof here. Here's what we're proving. Let beta be a basis on X. If B1, B2, ... Bn are all basis elements such that X is in their intersection, then there must exist some other basis element such that X is in that other basis element, and that other basis element is a subset of their intersection. Pictorially, what am I saying? I'm saying if you have, here's a basis element, here's a basis element, here's a basis element, here's a basis element. Notice that they all intersect, right? They all intersect this space right here. So if there's something in their intersection, namely X, then there must be some other basis element containing X that's a subset of all those sets intersection. I'm going to prove this by induction. So I'm going to prove that it's true when 2 sets intersect. And then I'm going to show you that if it works when k sets intersect, it also works when k plus 1 sets intersect. And therefore, it works for any number of intersecting sets. So I'm going to show you that it's true when we're talking about two sets intersecting. And that if it's true when k sets intersect, then it's also true when k plus 1 sets intersect. And therefore, it's true when 3 sets intersect, and 4, and 5, and 6, ... And therefore, for any number n, for any finite number n you choose, if they all intersect, then this property is going to hold. So that's big picture thinking what we're doing here. Now, proofs by induction, they can be dense the first few times you see them, so try and get more focus on the big idea than rather focusing on the notation. So first, I'm showing that 2 makes the statement true. So, 1. We call the number that we're starting with here our base case. Now, let your reader know, hey, we're doing proof by induction. So I say base case. That's what B dot C dot here means, sorry. Common stuff. Base case. For n equal to 2, so I'm saying 2 is going to be my base case. I'm going to show you the statement's true for 2. If x is in the intersection of 2 basis elements, then by definition of a basis, beta, there must exist some other basis element called b prime, such that x is in b prime is a subset of their intersection. That was the second property for basis elements. Second property for basis elements was anytime 2 of them intersect, pick a point in their intersection, there must be a third basis element containing it, where that third basis element is a subset of the intersection. So we have that by definition. So our 2's handled. Now I need to show that if it's true when k basis elements intersect, it's also true when k plus 1 basis elements intersect. So I need to show that if the statement is true for k, it's also true for k plus 1. So we know it's true when I replace the n with the 2 there. Now I need to show that if it's true when I replace it with the k, it's also true when I replace it with the k plus 1. So I need to show it being true for k implies it's true for k plus 1. So I'm proving an implication. How do we prove an implication? Assume the antecedent and show that implies the conclusion. So next, assume the antecedent. Assume that for n equal to k, if x is in the intersection of k basis elements, then there must exist some other basis element such that x is in that other basis element, and that other basis element is a subset of the intersection. So assume that if I have k of them that intersect, and there's some point in their intersection, little x, then there must be some basis element containing little x that's also a subset of their intersection. Assume it's true for k, show that means it's true for k plus 1. And then since we know it's true for 2, that means it's true for 3. Since we know it's true for 3, that means it's true for 4. Since we know it's true for 4, that means it's true for 5, etc. Okay, so assume that. Now, let x be in the intersection of k plus 1 basis elements. So I've got k plus 1 basis elements, and x is something in their intersection. In other words, x is in the intersection of k basis elements intersected with the k plus 1 basis element. This is just rewriting this a little bit different. The intersection from I equals 1 to k plus 1 is the same thing as the intersection from I equals 1 to k intersected with k plus 1. Let's maybe write out a concrete case here really quick. Help you with notation. This is just for the sake of notation. If I were to say the intersection from I equals 1 to 5 of a sub I, what concretely does that mean? That means a sub 1 intersected with a sub 2, intersected with a sub 3, intersected with a sub 4, intersected with a sub 5. Right? So all I'm saying on that line is, notice that the intersection from I equals 1 to 5 of a sub I is the same thing as the intersection from I equals 1 to 4 of a sub I, all intersected with a sub 5. Because this is just shorthand for these 4. And then intersected with a sub 5, we leave there. So the intersection from I equals 1 to k plus 1 of b sub I is equal to the intersection from I I equals 1 to k of b sub I intersected with b sub k plus 1. So I'm just removing the last one from that. Same thing I did going from here to here. So if x is in the intersection of those k plus 1 basis elements, it must be in the intersection of those k basis elements together with the k plus 1 basis element. Right? Now we know by assumption that if x is in the intersection of k basis elements, then there must exist some third basis element, we'll call it b star, such that x is in b star is a subset of the intersection of k basis elements. That's what we assumed. Assume for n equal to k that if n is in the intersection of k basis elements, there must be some other basis element containing x, where that other basis element is a subset of the intersection of our k basis elements. Dead sinking.
Remind me the star.
We're just naming it. I'm just making up a name right now. So since x is in the intersection of k basis elements, then there must exist some other basis element. I'm calling it b star. I could call it b prime. I could call it Henry. We can call it whatever we want. I call it b star. There must exist some other basis element. I'm choosing to call it b star, such that x is in b star, and b star is a subset of the intersection of all our basis elements. That's what we assumed right here. Except for when I said assume, I called it b prime here. Here I called it b star. Just naming the basis element that x is in.
Don't you normally name it at the bottom?
We usually use subscripts when we're iterating over something. This isn't iterating over anything. It's just a random one out there that satisfies this property.
Generally, if you're labeling things, you just put a label or a symbol on the top left to indicate that.
Yeah, so typically if you want something similar to something you're talking about but different, similar but not equal, then a common thing to do is just quickly give it a prime. So a b, a basis element, and some other basis element b prime would be a common thing to do. You wouldn't use subscripts unless you were talking about some collection of them. Then you talk about b1, b2, b3, b4.
Now, is that supposed to be a 1?
No, no, that was a b and then a b prime.
Yeah. Okay.
Like a, how did I just lose it? Thank you, apostrophe. Oh, I guess that prime notation also is from calculus. Sorry. Common thing we do in calculus. Hard to keep track of everyone's math background. It's hard to remember when you pick up on something. Like when you learned how to say, when you learned what the word because is. You gotta remember, oh, I'm talking to people this young. They don't know the word because. But these guys, okay, now it's okay. I don't know. That was probably a bad example.
Go bring it up if you don't know.
Yes, always bring it up if you don't know. We're not in a rush to get through this material. We don't have some semester deadline. So we can take all the time we want. That's one of the nice things about doing the classes like this. Okay. So since x is in the intersection of k basis elements, then there must exist, by assumption, there must exist some other basis element containing x where that other basis element is a subset of the intersection of the k basis elements. So in other words, x is in b sub star intersected with b sub k plus 1, which is just going to be a subset of the intersection of all our sets. Because b star is an intersection, is a subset of the first k intersections. So b star, I should have probably written it like this. This is a subset of, let's see, we'll use brackets here. A subset of the intersection from I equals 1 to k of b sub I, all intersected with b sub k plus 1. K plus 1, not x plus 1. We didn't need that bracket. Since b star is a subset of this set, then b star intersected with b sub k plus 1 is a subset of this set intersected with b sub k plus 1. And this is exactly equal to, now we're out of space here, make this b prime a little smaller, b prime. This is exactly equal to the intersection from I equals 1 to k plus 1 of b sub I. That's exactly what that's equal to. Here's the first k of them. Here's the k plus 1th of them. What did we do? We intersected all the ones from 1 to k plus 1. So what did I show? I just barely showed that x is in b star intersected with b sub k plus 1, which is a subset of the intersection of all our basis elements. Now, by definition of a basis, if x is in the intersection of two basis elements, what do we know? If x is in the intersection of two basis elements, what do we know?
Intersection.
So B1, B2 intersect. Their intersection contains subpoint x. What do I know? There must exist some other basis around it containing x, where that other basis is a subset of the intersection. Go ahead.
Can that basis around x just contain x?
It depends on your basis. If your basis was this topology, this basis, then yes. If it was a standard one, no. You can't have a singleton basis. So it depends on your basis. So up there we have B star we know is a basis element. So here's B star. And we have B sub k plus 1 we know is a basis element. And we know that x is in their intersection. So there must exist some other basis. That's the one we're going to call B sub prime, containing x. That's also a subset of their intersection. So since x is in the intersection of those two basis elements, then there must exist some other basis element, we're calling it B sub prime, such that x is in B sub prime is a subset of the intersection. And then, since this intersection is a subset of this intersection, we put all that together. X is in B sub prime, which is a subset of this intersection, but that's just a subset of the intersection of all the basis elements from 1 to k plus 1. And so it holds for n equal to k plus 1. Take the intersection of k plus 1, then it is the case. If x is in the intersection of k plus 1 basis elements, then there exists some other basis element such that x is in that other basis element. It's a subset of the intersection of the k plus 1 basis elements. So I showed it's true for k, and I showed it's true for 2, and then I showed that if it's true for k basis elements, it's also true for k plus 1. So we just showed that for any number of basis elements you choose, any finite number, it doesn't matter how many, any finite number, take their intersection. If they intersect, so if there's something in their intersection, like little x, then there must be some other basis element, we always call it B prime, containing x that's a subset of all the intersections. Bit dense. So that's proof by induction. That's a tough one for the first time you've seen proof by induction. Usually we do nice things with natural numbers, like proving 1 plus 2 plus 3 plus 4 plus 5 ... is equal to n times n plus 1 all over 2. Much easier proof. But if you can even kind of get this one, you'll be fine when we get to that in discrete math. We'll have to do discrete math with you guys. This is too good of a setup. Geometry and discrete math. That'll be a good year.
Point where we just take your word for it.
Well, some of you know, the ones I teach longer. Miss Emma, she's probably the one I've taught the most. Okay. So now the big proof of the class. No, that was a lemma. Lemma. What's a lemma? It's a small side proof to help you prove the main proof. Now in this case, since a small side proof happened to be a proof by induction, it actually felt like a big proof. But most people look at proof by induction as a small side proof. So I actually think that this one will be easier for you to follow than that one, since proof by induction is hard the first time you come across it. Okay, so now what are we proving? So thus far we've been talking about the topology generated by a basis, and we just called it a topology. We never proved that that was in fact a topology, so that's what our next proof here is that the topology generated by a basis is in fact a topology. Okay, so let's get at it. If we're going to prove that something's a topology, what do we have to show? Yeah, first thing we need to show is that the empty set and the entire set X are in. So let's show that first. 1. So we're going to start it here. What are we proving? We're proving that the topology tau generated by basis beta on X is a topology. So 1. Let
Prove that topology is topology.
we've been calling it a topology, but we never actually showed it was a topology. So now we actually need to take the time to prove it's a topology. Because what we want to do was give you examples of it before we actually proved it. So that's why we started working with it as a topology before we ever proved it was a topology. So now we need to actually prove it's a topology. So let beta be a basis on X, comma, and let tau be the topology. Remember, we're just calling it that. We need to prove it's topology. The topology generated by beta. Okay, so we need to prove tau is in fact a topology. I need to show that the empty set's in there. I need to show that the entire set X is in there. 2. Observe the empty set is in there. How do I know the empty set's in there?
Because bases do that.
Because by definition of a basis, by definition of a topology generated by a basis, we include the empty set and any union of basis elements. So the empty set is in tau, and the entire set X is in tau. How do I know the entire set X is in tau? Because it's a union of your basis. Union up your basis, you get all of X. That comes from the first property of a basis. For every little x and big X, there must exist a basis element containing that X. So X is equal to the union of beta is in tau. So I know that the empty set is in there, and I know that the entire set X is in there. Now what do I need to show? So now I need to show property 2. No, so far we just did property 1. Oh, you're saying can we skip to 3? Yeah, 3 is easy as well. Property 2 is the hard one to show here. So now we need to show property 2. Property 2 says that for any finite collection of open sets we choose, we need to show that their intersection is also an open set. So to prove this one, I need to I'm going to let V equal the intersection from I equals 1 to n of u sub I, comma, where each u sub I is in tau. So let V equal the intersection of finitely many open sets. I need to prove that V is open.
Isn't any intersection of open sets?
Yes. In a topology, yes. I need to prove that this thing tau is in fact a topology. So I need to show it has that exact property that you're saying. So that's what we're trying to show. So let V be the intersection of finitely many open sets. Or finitely many things in tau. How many? 10, 20? I don't know. Finitely many. Which ones? We don't know. But we know that they're in tau. And there's a finite number of them. The actual set itself might be infinite. The n here is some number. Could be 1,276. It's some number. So we've got some intersection of open sets. Some finite intersection of open sets. What do I know about each open set? What do I know about each one of these u's? They're in tau. And how do we get sets in tau? Tau is a set of, what do we know is in tau? It has the empty set and any union of basis elements. We know that it's a basis. Tau is what we generated from our basis. So what does our basis give us? It gives us the empty set and any union of basis elements. So yeah, 3 is going to be trivial. 2 is a hard one. So each u sub I here is a union of basis elements. Each u sub I is a union of basis elements. Each open set, pick any open set out of tau. So here's a random open set out of tau, call it u. U has to be equal to some union of basis elements. This one might be equal to B1 unioned with B3 unioned with B2796. Those basis elements. If we were to list out all our basis elements of beta.
You can't just be B2796.
It could have also just been this basis element. Maybe use just one basis element. Maybe it's 2 basis elements union together. Maybe it's 17 of them union together. Maybe it's all of them union together. Whatever U is, it has to be a union of basis elements. That's what every open set is in the topology generated by a basis. It's a union of basis elements. So let V be the intersection of some finite number of open sets, where each of those are open, and observe that if V is equal to the empty set, then we already know that it's in tau. So if when we take all those intersections we get nothing, then we already know that we're an open set. Because the empty set we already showed is open. That's the first thing we did. So if you happen to be unioning together this open, or intersecting this open set with this open set with this open set, what do you get? The empty set. So we handled the case where you happen to pick sets that don't have an intersection. Now we're going to handle the case where you pick sets that do actually have an intersection. If they actually have an intersection, that means they have at least one thing in their intersection. And we're going to call that one thing X. So if they happen to overlap, if they all happen to overlap, then there has to be at least one thing in their overlap. And we're going to call that one thing in their overlap little x. So we've already handled the case where V is empty. 4. Assume V is not empty. Or in other words, assume that there exists some little element x in V. If little x is in V, what does that mean?
There's another basis element.
Well, you skipped a step there, but yeah, that's where we're going. V is an intersection of open sets. So if x is in V, then x is in the intersection of all these open sets, which means x is in every single one of those open sets. So let's draw a picture again. So here's u sub 1, here's u sub 2, here's u sub 3, here's u sub 4. If we take the intersection of all of them, we get this set right here. Right? This is the one that's the intersection of all of them. That's what we're calling V. If something is in V, like little x, then it must be in u sub 1, and it must be in u sub 2, and it must be in u sub 3, and it must be in u sub 4. Because it's in the intersection of all of them. Make sense? And if it's in all those open sets, remember that U1 is composed of a union of basis elements. And U2 is a union of basis elements, and U3 and U4. So if it's in U1, then there must have been some basis element that works towards building U1, call it B1, that contains X. And since it's in U2, then there must be some basis element that we used to build U2. Maybe in that case it was a whole set itself, B2, that contains X. And for U3, there must be some, maybe B3 is that small, B3 inside of U3 that contains X. And maybe B4 is also the same size as U sub 4. So what I'm trying to say with that picture is that assume V is in there, which means that assume V is not empty, which means that there exists X in V. That means that for all U sub I, comma, X is in U sub I. which means that for all u sub I, comma, there exists b sub I in beta such that x is in b sub I. Because u sub I is just a union of basis elements. And so one of the basis elements that went towards building u sub I, which we're calling b sub I, must have contained x. Which gives us that x is in the intersection of all those basis elements from I equals 1 to n of b sub I. Now using our previous lemma, that means that there must exist some basis element containing x that's a subset of all those intersections. But all those intersections are going to be a subset of V. Perfect. So x is in the intersection of all those sets, which gives me by the previous theorem, that there exists B prime in beta such that x is in B prime, which is a subset of the intersection from I equals 1 to n of b sub I, which is a subset of the intersection from I equals 1 to n of u sub I, which is equal to V. Each basis element was just a piece of the open set. Maybe the whole open set, maybe just a piece of it. So each basis element is for sure smaller or equal to the open set it came from. So we got x is in B prime, which is a subset of the intersection of all the basis elements, which is a subset of the intersection of all the open sets, which is V. So in other words, I showed that there exists some set B prime such that x is in B prime, and B prime is a subset of the intersection of our sets. That's the best way to say it now. Rather than calling this B prime, will this be too nuts? Maybe I'll just say it. Maybe I'm overthinking it. So I just really showed that for any x in V you grab, I found an open set containing x that's a subset of V. So I can now repeat this whole process for another point x and b and find another b prime. So I'll call this b prime x. Let's call that b prime x. B prime. Where did I say it? Then for all u, there exists bi in beta such that x is in bi, which is at, oh, it's just right here, right in front of my face. So there exists b prime sub x in beta such that x is in b prime sub x is a subset of V. Now pick another point x and v and do the same thing. And we get another basis element containing that point, another basis element containing that point. So ultimately, what did we do? Let's draw a picture for it really quick. Here's V. Here's x. I showed how for any x you get, we can find some basis element containing x that's also a subset of V. Pick a different point in V, y, we can find a basis element containing that point. That's a subset of V. If we do that for every single point in B, V, getting all those basis elements, then the union of all those basis elements is B. Is V. Sorry. Let's say W, and let me say it again so I'm not accidentally confusing you. W. Pretend that we did W here. So you don't get confused when I'm saying V versus B. All right, so W. So here's W. What did we just really show? I showed how for any point x in W you choose, I can find a basis element containing that point where that basis element is also a subset of W. And since we can do that for any point, so this was b sub x, if this is y, sorry, b sub x prime, this was b sub y prime. If this was z, then we could have found a b sub z prime. We can do it for any point in W. And so then W is just a union of those basis elements. All right. Then, I don't know how else to say this. Then W is equal to the union for every little x in W of B prime sub x. So we union up all those basis elements for each point in W, and that gives us W. And since W is a union of basis elements, that gives me that W is in tau. Okay, that's a hard one. Now we need to show the last property of a topology. That if we have some arbitrary collection of union sets, if we have some arbitrary collection of open sets, then their union is also an open set. Yeah, almost. Let U sub alpha be any random subset of our topology. So it's any collection of open sets. And I need to show that its union is open. But since each U sub alpha is a union of basis elements of, I'll use BE for basis elements, comma, then so is the union of all the U sub alphas. Each one of those open sets is a union of basis elements. Union up all those open sets is still a union of basis elements. So is a union of U sub alpha, which gives us that it's in tau. And square box. There we go. Showed the three properties. Sorry, got tight on space. Squiggly line, squarish box. All right. That was quite a tough one to follow. Tough proof. One of the harder proofs we'll have for a bit. And now we can kind of take a step back and just get more comfortable with this stuff with some examples. Okay. Oh, I think we have one more easy proof. Hopefully it's easy because I only gave myself a little space. Oh, move camera. Let's see. Just so I know. I guess I start scribbling over here. I think I can go that far. Okay. Let beta be a basis on X, then U is open if and only if for every point in U there exists some basis element such that X is in that basis element and that basis element is a subset of U. We've almost proved this exact thing. Come back to what we proved last time. What did we prove last time? Let A be any subset of X, then A is open if and only if for every point in A there exists an open set in tau such that X is in that open set as a subset of A. It's almost the exact same proof. But now we're just using a basis element rather than an open set. But a basis element is an open set. Almost. That takes care of one direction. So we've already proved one direction. Oh no, we proved both directions. That's literally just a special case of that proof. Right? So if we have any set U, oh wait, no, we still need to prove it. The direction I need to prove is, so one direction is obvious. Let's kind of write it out so that we can think about this. Make sure we're not making any assumptions. But it's going to be really close to that same thing if we don't already have it for free. I'm still not convinced. So let's prove it one way. So let's prove it this way first. Let U be open. So if U is an open set, what do I know? Let U be open.
Where's the topology?
Okay. We assume we have a topology. The topology generated by beta. So let beta be a basis on X and let tau be the topology generated by beta on X. Okay. That all goes without saying. Obviously not. Okay. So then let U be open. What do we know about U? It's in the topology, but how did we build our topology? We unioned up basis elements.
So use base.
No. Right. U is equal to some union of basis elements. Maybe it's easier to just write. Well, then for every X in U, comma, there must exist some basis element such that X is in that basis element. Because all the elements of U came from a basis element. So if you grab some element in U, it must have been in some basis element. Because U is a union of basis elements. So here's U. If I not use an open set, it's a union of some basis elements. So it could be this basis element together with this basis element together with this basis element. If X is a point in there, it must have belonged to some basis element. Otherwise, how else did it get in U? So let U be open, then for every point in X, there must exist some basis element containing that point.
So what is B of X?
B sub X?
Neighborhood.
Oh, it is a neighborhood. Because all your basis elements are open sets.
Neighborhood is just basis. There's just something containing
A neighborhood is an open set containing X. So not only is there an open set containing X, but there's a basis containing X.
There's this basis as in basis. Basis element X and basis. Such that X basis
Is in B sub X. There must exist some basis element called B sub X, such that X is in that basis element. Because how else did it get in U? Because U is a union of basis elements. So every element that's in U must have been a basis element. Which one? I don't know. For X, we'll call it B sub X. But there must have been at least one. It might be in multiple, might be in thousands, might be in millions, might be in infinitely many basis elements, but it has to show up in at least one. Otherwise, it couldn't have gotten in U. Okay, so that way's easy. Oh, and this way we get by the union lemma. 2. Now, assume for all X in U, comma, there exists B sub X in beta such that X is in B sub X is a subset of U. 3. Then U is just equal to the union of all those basis elements. U is equal to the union for every X in U of that corresponding B sub X. Which gives me that U is open, because it's a union of basis elements. So this is a reverse way. This is saying, here's our set U. Let's assume for any point in there you choose, I can find a basis element containing that point. That's still a subset of U. And for this point, I can find a basis element. For this point, I can find a basis element. For this point, I can find a basis element. Union up all the basis elements, you get U. Because you can't get more than U because each basis element was a subset of U. And you have to get all of U because we have a basis element for every point in U. Okay. So kind of square box. A lot more talking than showing. All right. Okay. And then, before we did this, guys, some of you hadn't seen yet. Maybe we'll just move this, and then I can rewrite that out as needed. We're going to have to take a geometry break here for a sec. What? These guys haven't gone through the proof of the Pythagorean theorem. And then so with that, we also need the distance formula. And if you're not comfortable with the distance formula, you're going to struggle with the standard topology on R2. Huh? Okay, I think that's good enough. Don't want to spend too much time messing with it. So let's do Pythagorean theorem real quick. You comfortable with the fact that the angle sum in any triangle is 180 degrees? Or do we need to do that one real quick? No. So if you're asking, then probably not comfortable with it. So let's do that one really quick. First off, 180 degrees, what is that? That's the angle of a straight line. That's what we mean by 180 degrees. So let me show that the angle sum of a triangle is the same as a straight line. So here's what we're going to do. We're going to start with any arbitrary triangle. Doesn't matter which one we use. Oops. Some random triangle. That's not meant to be a right triangle necessarily. Pick one of the sides, doesn't matter which one, and create a line through that side. I'm going to pick that side because of obviously how I drew it. That's the easiest way to go. But I could have reoriented my triangle and did it that way or on that side. Doesn't matter. Now, through the opposite vertex, draw a line parallel to the given line. So we're in trouble with my art skills. Those are parallel. Now extend each of these lines some, enough that we can see angles. If I draw this half decent, some of the stuff would jump out at you. Okay, notice, since these two lines are parallel, then the angle that this line makes with this line is the same as the angle this line makes with this line. So in other words, this angle has to be the same big as this angle, because this line's parallel to this line. So whatever angle it makes with this line is the same angle it makes with this line. My picture's lying a little bit because I'm not drawing very straight. You with me? Similarly, this angle has to be the same big as this angle. You see that? And then finally, this corresponding angle has to be the same size as this corresponding angle. So we've called this alpha, beta, gamma. Notice that this is beta, gamma, alpha. What's alpha plus beta plus gamma? 180 degrees. So alpha plus beta plus gamma, 180 degrees. Doesn't matter your triangle. Okay. Now Pythagorean theorem really quick. Pythagorean theorem, we're going to draw two squares. Try and draw them the same size. I'm going to need a little bit of space right between them probably. Okay. This is going to be perfect. Hopefully it's close enough that you can see the picture. Okay, so this right here, we're calling this distance from here to this point little a, the distance from here to this point little b. And I'm trying to construct it so that this is also little a, this is little b, this is little a, this is little b, this is little a, this is little b. With me? Similarly over here, this is meant to be little a, b, a, b, b, a, b, a. Now, what is the area of this square? It's this distance times this distance, right? So it's a plus b, that's this length, and then squared. That's why we call that squaring. This is how a Greek would have represented a plus b squared. They didn't have algebraic notation like we have. So this has area a plus b squared. Notice, what does this have? A plus b squared. Same thing. So they have the same area. Now we can break up their area. We'll focus on this one for a second. What's the area of this piece? A times b, length times width, right? What's the area of this? B squared. What's the area of this? A times b. And what's the area of this? A squared. Oops, b squared. And so this is equal to a squared, and then we have two of these ab's, and then we have b squared. And so this is how Euclid would have proved that a plus b squared is equal to a squared plus 2ab plus b squared. All right, now let's come back and look at this picture over here. So looking at this picture over here, I'm going to connect each of these, if I can. Now, since this is a square, we know that each of these are right angles, right? Okay. And now we know, oh, I don't even need to use angle sums. One of your congruence relations is side angle side. Right? Side angle side. So I know that this triangle is congruent to this triangle, is congruent to this triangle, is congruent to this triangle. So I know this angle is the same as this angle, is the same as this angle, is the same as this angle. And I know that this angle is the same as this angle, is the same as this angle, is the same as this angle. Now, focusing on just one of these pictures for a second. If we call it the smaller angle alpha and the bigger angle beta here, then alpha plus beta plus a right angle has to be 180 degrees. So alpha plus beta has to be 90 degrees. Or in other words, here's what I'm trying to get at actually. So that's alpha, that's beta. Alpha plus beta plus this missing chunk have to be 180 degrees. Alpha plus beta is 90 degrees, so this missing chunk right here has to be 90 degrees. So this right here is a right angle. Well, we need to argue it's a square. It could have just been a rhombus. So we prove that each of those are right angles. Similarly, if we call this side length C, since all these triangles are congruent, then this is also C, this is also C, this is also C. And so now it is for sure a square with side length C. Now we're positive of that. So the area of this inner square is C squared, right? What's the area of one of these triangles? Half the base times the height, right? 1/2 AB. So the area of the whole square is equal to, how many of these triangles do we have? 4. So I have 4 1/2 ABs, or in other words, I have 2 AB. You see that? And then the area of the inner square, which is C squared. So I know this is equal to this. So in other words, I know C squared plus 2AB is equal to A squared plus 2AB plus B squared. Cancel out the 2 ABs on both sides, and you get C squared is equal to A squared plus B squared. So that only works with right triangles. What did we just really show? We just really showed if you have some right triangle. Here's a right triangle. This is A, this is B, this is C. If I were to create a square using that side length, and a square using that side length, and a square using the hypotenuse, then the area of this square plus the area of this square gives me the area of this square. A squared plus B squared is equal to C squared. That's what we proved. Oh, it's crazy. There's nothing intuitive about that. It's an amazing proof. Okay.
How did Pythagorean discover that?
Who knows? Okay, so now we need to go to the distance formula. Let's do one concrete example of this really quick. So, concrete example. If I have a right triangle, and I tell you that this length is 4, and this length is 3, what's this length? 5. What did he think in his head? He said 4 squared plus 3 squared has to equal 5 squared. If this were x, let's see how we solve this in general. We'll pick numbers this time that he can't do in his head. All right, so we'll pick 11 and 12. What's x? You guys are way overthinking. The point is, I know that x squared is equal to 11 squared plus 12 squared, right? Or in other words, x is equal to the square root of 11 squared plus 12 squared. Who cares what they are?
20. What?
That's the answer. You can simplify it if you want. It's going to be x is equal to the square root of, what's 11 squared? What's 12 squared? What's 144 plus 121? 265. All right.
What's that? Is that,
You're saying what perfect squares go into there? There probably isn't one.
yeah.
Well, nothing goes into it evenly, but I don't know. Like, you might be able to factor out a 9 with a 3 or something.
How does it prove that right angle is actually right angle?
If it satisfies the Pythagorean theorem, then it has to be a right angle. But we were saying given a right triangle, where the legs are this length, find the hypotenuse. So it was given that was a right triangle. This only works for right triangles. To do it more general, we have to use what's called the law of cosines. And I'm not going to derive that for you right now. We can do that when we do geometry, at the end of geometry. Okay, anyways, so there's that. So, now the other thing we need to go over was the distance formula, which uses the Pythagorean theorem. So, you're used to the xy plane? Okay, so if I have any 2 points on the xy plane, what's the distance between those points? We're going to come up with the formula really quick. It'll be easy. That gives you the slope. Slope?
Well, no, it's not though. Wouldn't it be the rise?
Okay, look, we'll just do it. We don't need to guess. Okay, so here's some random point. Don't read too much into the picture. It has coordinates x1, comma, y1. So we got some point. Let me center better. We got some point with coordinates x1, comma, y1. And we've got some other random point up here with coordinates x2, comma, y2. I'm looking for the distance between them, right? I want to know what's this distance. Well, we can construct a little dummy right triangle here. Right? And what is this length? It's x2 minus x1. It's the x coordinate of this point minus the x coordinate of this point. Is it appealing to everyone's intuition how that gives you the distance? If I want to know the distance between you and my mug here, and I know that this mug is a meter away, and I know that you're 6 meters away, how far are you from the mug? 5 meters away. I do the distance from you to me minus the distance from me to the mug, leaves me the distance from the mug to you. Same thing. x2 is this distance, x1 is this distance. That's what the x-coordinate means. It means how far away you are from the y-axis. So this distance is x1, this distance is x2. This distance is x2 minus x1. Take x2, minus off that piece, we're left with that. Perfect. There we go. That's what I want to see. Okay. And the height is y2 minus y1. y2 is that height, y1 is that height. If you want that, you take y2, minus off that piece, and we're left with that piece. Okay. Now we use Pythagorean theorem. So this is d, what we're looking for, d. So we know that d squared is equal to this distance squared, which is x2 minus x1 squared, plus y2 minus y1. Sorry, that was a bad y. Or in other words, our distance d is equal to the square root of x2 minus x1 squared plus y2 minus y1 squared. No. You can't do anything more with that. That's the distance formula. So that gives you the distance between any two coordinate points you want. Make sense? Okay. We're pushed for time, aren't we? Yeah. So let me just say high level what the standard topology on R2 is going to be, and it's what we'll come back to next. So R2, when I say R2, what do I mean?
The second vector.
I mean the real number plane. R2 is what we were working with right here. We're in R2. R cross R. R cross R is all the points, all the order pairs you can make with two real numbers, which is the real number plane. So R2 is the real number plane. That's what we've been working with this whole time. The standard topology in R2, our basis for our topology, is going to be all the open balls you can make. And we're going to draw them with dotted lines like that. When we draw dotted lines like that, that means not including the border, but everything inside. So it includes all the points inside, not including their border. And that's going to be a basis element. All these open balls. Anything you can create with these open balls. And so some open set like this is going to be open in the standard topology on R2. Because I can use the open ball that gives me this little piece, union together with the open ball that gives me this little piece. I can take infinitely many open balls, getting them, fitting that as well as I want, union them all up, and it's going to give me that. Turns out just about any shape you can draw on the whiteboard where you don't include its border is going to be an open set in the standard topology on R2. And so that's why it becomes standard when you're trying to draw an arbitrary open set to use dotted lines rather than filled in lines. And down the road, we'll start using filled in lines to draw what we call closed sets. What's a closed set? We'll get there. That's the next section. No, a set can be both open and closed. We call it flopen. So it's just not in the standard topology. We typically draw open sets and closed sets this way because we're typically thinking about the standard topology on R2. On R2, a set can't be both open and closed, except for R and except for the whole plane and the empty set. Those are the only ones that are both open and closed.
When you say open set in this context, you're referring to all of the sets. Topology as open set in that same way.
Yep. So in the standard topology on R2, any shape you can draw where you don't include its border, so you include all the points but not the exact border of it, that is going to be an open set. Turns out that's what it's going to be on R2. On R1, it's any open figure you can draw where you don't include the border points. So on R1, when we're talking about the real number line, I could do don't include this point, but all the points in between, together with don't include this point, but all the points in between, together with don't include this point, but all the points in between. And that's any picture I can draw on R1 without including its endpoints. Standard topology on R2 is going to be any two-dimensional thing you can draw without including its endpoints. Standard topology in R3 is going to be any closed surface you can create, not including the actual surface, but all the points inside. And you generalize to R4, R5, R6. And so it's real easy to talk about topology in 8 dimensions of space. Huh?
Analyze it.
You can't even draw or something.
You can draw whatever you want. But it's very hard to get any close to intuition for higher dimensions. My goodness. Huh?
Have you done any math studying that?
Oh, tons of math working with higher dimensions. It's easy mathematically to work with them. So a vector in 2 dimensions, like this, a vector in 2 dimensions. So here's a vector in 2 dimensions, right? And that would be the vector 1, 2. It went over 1, up 2. A vector in 3 dimensions, if that was my origin, that bottom corner of the classroom over there, the vector that pointed to here might have gone, I don't know, 5 meters in the x direction, 1 in the y, 1 in the z. So we would represent that with the vector 5, 1, 1. Well, if I want to talk about a 6-dimensional vector, maybe we went 4 units in the u dimension or the t dimension or whatever. So mathematically writing it out, that's real easy. Getting any intuition for this stuff is a whole nother beast. I mean, it's hard for us to even sometimes go to the lower dimensions.
So do you have the intuition for our board?
I have some intuition for our board. So I know that if we were a 3-dimensional space as a subspace of a 4-dimensional universe, a 4-dimensional being would be able to see inside my intestines right now. They can see inside everything. Here's how you can make sense of that. It's not that they have X-ray vision. It's that they're looking through the other dimension you can't think of. So imagine for a second you're a 2-dimensional being. You exist in this whiteboard right here. So here you are. You're that dot. Here's your best friend Frank. He's that dot. You guys only comprehend 2 dimensions. You only know going this way, that way, that way. You have no concept of outside the whiteboard. You built yourself a nice room. And it has a door on it. That's a little segment that you can close. You can close that door so that someone can't come in your room. Well, you got parts on you. Whatever. There you go. And he's got parts on him. So you reach over, you take that, and you close it. Now Frank can't see you. It doesn't matter how Frank moves around in this space. No matter where he goes, he can't see you. But you can see him just fine. Because this is... No. We can all see what's happening. Because this is 2-dimensional space embedded in a 3-dimensional universe. And so if we're 3 dimensions of space embedded in a 4-dimensional universe, we can close off someone seeing us from all the dimensions we can see. But we can only look these directions, the same way he can only look around this way. We think we look all around. No, we forgot that way. The one way that we can't point. And thinking about direction in the way you can't point, that's a hard thing to think of. Hard to get intuition for.
What would be closed in R5?
Huh?
What would be closed in R4 so R5? Yeah. That's what we're going to think about.
Right, it's just another dimension.
You go online and look at what would a 6-dimensional world look like to a 2-dimensional being, and apply that same logic to what a 4-dimensional world would look like to a 3rd dimension. They've done YouTube representations of that.
Yeah, they try to do, because you can draw a 2D picture of 3-dimensional space. And so they try to do these 3D renderings of 4-dimensional space to try and help you get some intuition for it. And you can go look at stuff like that and see if anything clicks in your brain. But it's kind of hard to get intuition for it.
Well, some people will call it time.
What? Well, okay. Yes, in a sense. All right. So a dimension is really just a piece of data you need to figure out where something is. So if I want to know exactly where you are, I need to know 3 things. I need to know, if we're talking about on the Earth, I need to know your longitude, your latitude, and your altitude. And if I know those 3 things, I can go find you. Just give me your longitude and your latitude, and you really were 10 meters underground, I'm never going to find you. But if you give me longitude, latitude, and altitude, I can always find you. Right? If I have those 3 things, because we're in a 3-dimensional space. So 3 coordinates exactly describes where you are with respect to some reference frame. Kind of. Because what happens if you were there, then you left? So I also need to know the time. If I'm going to meet you, I need to know the place and time. So it takes 4 coordinates to specifically state where you are.
Don't you need motion on where you went during the time?
What?
Don't you need like where you went during the time? Just knowing the time.
If I know the exact location and the exact time, you and I can meet. Yes, I need those 4 things. I need longitude, latitude, altitude, and time, and then I can always meet together with you. So that's one way you can think about it. In general relativity, there's not a distinction really between space and time. Time is seen as another dimension. It's treated very much the same way space is treated, and objects are treated as if I were to handle you in general relativity, you would be like a kind of like a line segment, which is like your whole everywhere you were at every instant of time treated as one geometric figure. So you're born here, you go and you die here, and there's you. That's intuition. Another way to get intuition for how time is a 4th dimension. The only way we can picture this is if we're ready to map 3 dimensions of space onto 2 dimensions. So go with me here. Imagine that we project all 3-dimensional space down onto the surface of a ball. So that maps out space, the surface of that ball, and you have the different locations on it. Now this is actually kind of close to how we currently model our universe, kind of like the surface of the Earth. And so it turns out, with our current model of the universe, if you could go that way really, really, really fast, you'd eventually go around and come back and hit yourself. In our universe. Huh? There, okay. We can talk about the center of the universe. So, if we map the whole universe onto if we were to map it from 3 dimensions to 2 dimensions, it would leave us with the surface of the sphere. We'd be on the surface of a sphere, kind of like the surface of the Earth. You want to talk about the center of the universe, that's like talking about the center of the surface of the Earth. Where's the center of the surface of the Earth? Where's the center of the surface? Not the center of the sphere. We're talking about the surface. So all of 3D space is now just the surface of a sphere. Where's its center? It doesn't have one. It doesn't make sense to talk about the center of a surface of a sphere. Now, our universe isn't just modeled by the surface of a sphere, because our universe is expanding. So a better model for our universe is to think about it as being modeled on the surface of a balloon. And someone's blowing it up. So, if I were to draw 2 points on a balloon, and I start blowing it up, then it's going to look like those points are moving apart. Are they actually moving apart? No, it's that the rubber on the balloon is growing between them. Right? If I draw with ink a dot on a balloon, and draw with ink a dot somewhere else, and I blow up the balloon, the ink's not moving, it's holding still. Right? The ink's not moving around on the balloon, it's holding still on the balloon. But the rubber between them is growing. It's expanding. So, we say that galaxies are moving away from each other. No, the space between them is growing.
Yeah, okay.
So the universe is expanding, like the surface of a balloon expanding. And so if you run it backwards, this what you want to call the center of the balloon, so expanding the balloon out, that's the time direction. The universe is expanding in the direction of time. You run time backwards, the universe is getting smaller and smaller and smaller and smaller and smaller, all the way down to singularity, which we call the Big Bang. So that's the center that you were trying to talk about. So what's the center? The Big Bang, if you want to say that. But then you're saying, no, that happened forever ago. What's the center right now? Well, you're asking for the center of a surface of a sphere.
Right.
So the direction that the balloon is expanding in is the time direction. That's another way that you can think about as time is the 4th dimension.
So how do you not just go off the surface of the balloon?
It's really a 3-dimensional surface of a 4-dimensional sphere. We're not talking about a 2-dimensional surface of a 3-dimensional sphere. We're talking about a 3-dimensional surface of a 4-dimensional sphere. That's what we're talking about. Now that's going to break your intuition. So imagine that we just have 2 dimensions of space. Then we can start to picture things. So there's only 2 dimensions you can go off the surface, isn't one. If you're moving on the globe, so imagine you're a 2-dimensional being on the surface of the Earth. The only way you can travel is around the globe. If you're a 2-dimensional being on this globe, you can only go that way, that way, that way, or that way. You have no concept of going off the globe. You have no concept of drilling into the globe. You just move around on a surface. So here's the Milky Way. There you are. And you can only comprehend going that way, that way, that way, and that way. I don't know. Yes.
So, looking at a drawing,
Yep.
looking at a drawing in the fourth dimension would be like looking into, like,
Well, they could draw two-dimensionally if they want. We can create one-dimensional drawings if we want. Kind of. All right. Here's one dimension. And let's draw some one-dimensional objects. Well, here's this line segment. There we go. There's one object. Here's another object. A dot is zero-dimensional. A line is one-dimensional. A plane is two-dimensional. And the space is three-dimensional. So,
What class did you learn? What class did you learn this
I don't know.
so, if you,
Not quite. Definitely wasn't that.
if you had a drawing of a fourth, like, if somebody could create a drawing of a fourth dimensional, it was a fourth dimensional drawing, you could see, like, it'd kind of be like a movie where you could see different types. Not that we can think of, but.
Well, now you're trying to say where the fourth dimension is time. You can think about just 4 dimensions of space and not worry about trying to think about in time. I mean, if you're talking about a 4-dimensional being, what does a 4-dimensional being experience when they have 3 dimensions of space, 1 dimension at a time? Ask yourself. That's you. You are a 4-dimensional being with 3 dimensions of space and 1 dimension at a time.
Yeah, that makes sense. So it is the fourth dimension space time.
When we model space-time, it's a 4-dimensional manifold. 3 of those dimensions are space, 1 of those dimensions are time dimension. So there's 4 dimensions. So the 4th dimension of a space-time is time.
Oh, that's space-time?
Yeah. There's no reason that we can't just talk about some space where there's just 6 dimensions of space and there is no dimension of time. That's perfectly fine. So it's not the 4th dimension is time. It's when we model space-time, we use 4 dimensions. 3 of them are space, and the 4th one's time. That's what people mean when they say the 4th dimension is time.
A dimension is time.
1 of the 4 is time. 3 of the 4 is space.
Well, I'm saying there's more than 4 dimensions, so like,
You have
they're
3
not
dimensions
necessarily
of time.
numbered, right?
Space-time is modeled with 4 dimensions.
Yeah.
3 of them are space. 1, you're right. Calling 1 the first one and 1 the third one is completely arbitrary. We could have just as easily said the 2nd dimension's time. So you have your x direction, you have your time direction, you have your y direction, your z direction. Okay, those are your 4 dimensions. And the 2nd dimension's time.
So,
And there's nothing wrong with that.
theoretically, can you have 2 dimensions that are time? Like a theoretical space-time with 2 dimensions of space and 2-dimensional time.
There's no reason why you can't have that. Some beings that can navigate through time in a 2-dimensional way. Is there some other universe out there where beings experience time 2-dimensionally? I have no idea.
There's some other universe out there.
Yeah. That's long. Bro, that hurts me.
I mean, we'd also have to nail down what we mean by universe now.
But what I'm, you don't have to record this. I'm just.
Yeah, we're getting off topic of topology. We're gonna stop this.